Hi and Assalamualaikum to all students. In this video, we will talk about flows as stress concentrators. We know that the flows, stress concentrators, and stress will be concentrated at the crack of the tip. And if it is assumed that a crack is similar to an elliptical hole to a plate and is oriented perpendicular to the applied stress here, the maximum stress, the sigma m, occurs at the crack of the tip and may be approximated by this equation, where the rho t is the radius of a curvature of a crack tip. Sigma sub naught is the applied stress here, and sigma sub m is stress at the crack tip. This is what we call as a Griffith crack model. And these flows are determined to the fracture strength because an applied stress may be amplified or concentrated at the crack tip. The magnitude of this amplification will depend on the crack orientation and geometry. And this phenomenon is demonstrated in a figure here. A stress profile across a cross section containing an internal crack. Here we have an internal crack. As indicated by this profile, the magnitude of this localized stress will diminish with a distance away from the crack tip. So here we have a crack tip. We can see that the maximum, the magnitude of the localized stress as it decreases as it distance away from the crack tip here. So here is an example problem. The question says that what is the magnitude of the maximum stress that exists at the tip of an internal crack having a radius of a curvature of 2.5 times 10 to the power of a negative 4 millimeter, and a crack length equals to 2.5 times 10 to the power of a negative 2 millimeter when we apply stress of 170 megapascal. So what we want to find here is the maximum stress, maximum stress that exists at the tip of an internal crack. So here's the solution. We are given that the applied stress is equals to 170 megapascal, and sigma dot m is the stress at the crack tip that is we are going to find, or we are going to solve in this question. And the rho t is the radius of a curvature of crack tip equals to 2.5 times 10 to the power of a negative 4, or 10 to the power of a negative 5 inches. So this is the equation that we are going to employ in this question. So to find the stress at the crack tip, we just plug in the value. So 2 times 170 megapascal. 170 megapascal is the applied stress here, times 2.5 times 10 to the power of a negative 2 divided by 2. So why is this value divided by 2? Because we deal with an internal crack. So we have to divide the value by 2. If the crack is external or on the surface of the material, we can directly use the value without having to divide it by 2. And remember that the crack is assumed to have an elliptical shape. So 2.5 times 10 to the power of negative 2 divided by 2 divided by 2.5 times 10 to the power of a negative 4. This is the rho sub t, or the radius of a curvature, to the power of 1/2. And when we plug in the value, you calculate it, and what we get is the stress at the crack tip equals to 2,404 megapascal. Or if you use a customary unit, what you will get is 300,000 354,000 psi. So this is the answer if you use SI unit, and this is the answer that you will get if you use a customer unit. So we can see that the tip at the internal crack is 14 times compared to the stress that we applied, and this is the indication that the presence of stress magnified the stress by 400 times. So when we try to design a part, it is important for us to avoid a stress concentrator by avoiding a sharp corner. And how can we achieve that? It's by adding fillet to the corner. A stress concentration factor, or K sub T, is a dimensionless factor that what we use to quantify how concentrated the stress is in a material. So when the fillet radius is sharper, the more stress concentration, and it will eventually lead to a failure.